Hey, what's up, guys? Yeah, so today I'm going to talking about the Galois Main theorem and previous. If you haven't seen my Galois field theory list, and you can check out. Okay, so let me just start, and I hope you guys subscribe to my channel. So previously I just our settings that let's say f is a k is a finite extension. And previously, I proved that the order of the Galois group in this setting is bounded by the dimension. Okay. Okay, so the main theorem, I should say the right. So this is the lemma 1, and the main theorem in the Galois theory, which I'm going to prove in the next few videos, is that if you further assume that K is a Galois extension, so Galois extension means that a normal is separable, and you can prove that the Galois K over F is exactly the same as K over F. Okay, so this is the, I should say the, I would call it the main theorem, the first main theorem. Okay, and this proof is a little bit difficult. So in this video, I want to go into cheat a little bit. I want to use the Hertz's approach. Okay, so basically I add a simplification that I assume. So I further assume that the character K is 0. Okay, so if you assume character K is 0, then separable will be automatically trivial because the derivative has, I mean, you can prove this is what I already proved in the separable extension. So if you assume characteristic 0, then this would be easy to prove. Okay, so let's start to prove. Right, so in order to prove it, we need a very strange lemma that only works for the characteristic K. Okay, so lemma. Okay, so this lemma is very weird. This lemma says that if F, if the has a character 0, so basically the characteristic of this field 0, and the A and B are algebraic over K, or let's say or F, then there exists the C belongs to F at the joint with this AB, such that this FAB equals to FC, F at the joint C. Okay, so this is very weird. That's supposed. So this means that if you have a lot of roots and you add a characteristic 0 field, and actually this is the same as you find another strange number C, which you can add. Okay, so for example, let's say, so this is weird, right? For example, we take Q and you want to add a square root of 3, 2 and the square root of 3. And I think you can check that this is the same as you add a square root of 6. Okay, and the reason is that, I mean, sorry, sorry, I'm stupid. It's a square root of 2 plus square root of 3. Okay, the reason is that suppose you take x equals square root of 2 and the times square root of 3, and you square, you get 5 plus 2 square root of 6. Right, so that means square root of 6 belongs to Q square root of 2 plus square root of 3. And I mean, I guess you can further do the cube, right? If you further do a cube, then you will get something like square root of 2 and square root of 3, something plus this. And you can further keep doing, right? But then you can solve a linear equation to write square root of 2 in terms of square root of, you can write square root of 3 or square root of 2 in terms of x. Okay, so this is the strange example that actually if you take another lots of roots and add in the field f, then actually the same as you just add 1. So this is the simplifications. Okay, so let's prove. Okay, so idea is that let's say you can take f to be the minimum polynomial of A. So let me just write down minimal poly of A. Let's say this degree is m. Okay, and G is a minimum poly of B, and the degree f is n. Okay, so these are all the field, all f and G belongs to f bracket x. Okay, so now let's say f has a roots. let's say f has roots. If has roots, let's say a1, a2, out to am. Okay, and I let a1 to be a1 to be a, and g has the roots. Sorry, is roots. b1 the same as b, and b2 bn. Okay. And I want to find and so this is only finite of them, right? So let's take. So basically, if okay, so let's do this. Okay, so so let's do this. Let's try to find. Okay, let's try to find. So let's try to find a number. Let's say gamma, such that ai plus gamma bj do not equals to a plus gamma b. Okay, this looks weird, right? But for every ij. So basically, this just tell you that you want to find a gamma such that ai plus gamma bj will not the same as a plus gamma b for every ij. And it's easy to see that this gamma always exists, right? Because the character k, so the result is that this character f is 0, right? So which means that the f must at least has the infinity number, right? And if you see that ai plus, if you further assume that ai plus gamma bj the same as ai plus gamma b, then we can solve for gamma, right? So for every ij, there at most one gamma satisfies this equation, but your f has infinity not infinity elements, so gamma always exists. So gamma exists. Okay. Okay, so once you know the gamma exists, then you can define c equals to a plus gamma b, and you can claim that fab is the same as fc. Okay, so let's see the proof. Okay, so obviously that let's see a proof. So proof is so you see fc is a subset of fab, right? This is trivial because c is a linear combination of a and b, and right, and then we need to prove. So we just need to show that fab actually belongs to fc. Okay, so the idea is that right, we know that b has a minimum polynomial g. Okay, b has a minimum polynomial g, and let's see, that's this. Okay, so let's do this. Let's consider this h. Let's consider a function h of x. Okay, defined to be this f c minus gamma x. Okay, so right, so if you put this c is in f, right? So c plus c, right? So you draw this, right? And then you can see that h belongs to. Oh, by the way, let's define k to be f of c, right? So h of x belongs to k of x. And then we know that h of b is 0, right? fc minus gamma b, which is f of a, which is 0. Okay. So which means what? So this means that h of b and the g of b has and f of x and the g of x has a common factor, right? Has a common factor, right? But g is a minimum polynomial, right? So which tell you that so x minus b is in fact the greatest common divisor between these two, h of x and g of x. Okay, so what? Okay, so how should I? Okay, so yeah, this is so they have the same minimum polynomial. They have the comma roots. So let's say h of x and g of x is common. As common factor x minus b. Okay, and then you can and obviously that obviously that you know that you can check that if you plug h of bj for our j, right, you get f of c minus gamma bj, which cannot be gamma, cannot be a, right? Cannot be any ai, right? So this is non-zero. So which proves that the h and b, h do not have any kind of factors in the b, right? So and also G do not contain x minus b squared because G is a minimum polynomial. Okay. Right. So which tell you what? So I want to claim that h of x and g of x do not have any comma factor except for this one, right? So this is what I gonna do, what I already proved, right? Because g of x, all the other roots like b1, b2 up to any one will not be zero, right? Suppose j is not one. Okay. So finally, so what we gonna to show? What we already showed that h of x and the g of x only has a single comma factor. This is what we already proved. X minus b. Okay. So what? So that means by the theorem in the field theory, right? Your h of x, there exists the h of x and the g of x linear combination such their combination is x minus b. Right, so you can find a1 of x times h of x plus g of x times a2 of x, right, equals x minus b. Okay, so which tell you that the x minus b belongs to k of x, which tell you that b belongs to k of x. Sorry, tell you that b belongs to k, right, which is f of c. Okay, so what we are already proved that the b belongs to fc, then the rest is just to show that the a belongs to f of c. So we only need to show a belongs to f of c. Okay, so this is a simple fact, right? Because what? Because a is a c minus gamma b, right? So this belongs to f of c, and then this belongs to f of c, this belongs to f, right? So which tells you a belongs to f at the joint c. Okay. So we prove this theorem. Okay, so now we already have lemma. We already have the lemma. Then so that we can prove the theorem. Okay, so the Galois Main theorem in the character field 0 means, for example, so this theorem looks like if k is a normal extension. So remember that it's inseparable, right? So I don't need to worry about anything. I just need to worry about I just need to since I already got these results, right? So I only need to prove I don't care about separable, and I only need the normal and finite. Okay. Then I'm able to show that the Galois group of k of f, the order is the same as k f. Okay. So this is the technical, the idea that in the approach that the Hurston have, right? So this is a little simplification proof. Okay, so let's see the proof. Okay, so how should I prove? And okay, yeah. So I need to do a trick. Okay, so this is the trick. So let me just make a cheat. So let's cheat a little bit. So I can define a k as a normal extension. Okay, so now I change the definition of normal extension, but finally we will connect. So I can say that k is a normal extension of f. If k is a finite extension over f, if k is a finite extension. So this is the change of the definition. Finite extension of f, such that f is a fixed field of Galois kf. Okay, so yeah, so this is the cheat. Don't worry, I will try to fix in the next video. But this is cheat is that just tell you that if I say that k is normal extension f, it means that k is a finite extension of f such that f is a fixed. So this just means that if you take the fixed field of this Galois k over f, then you will get f. Okay, so I think that I already said in the previous video that the Galois theory try to get a one-to-one correspondence. So the idea, so our setting should be this is finite extension and the Galois. Now our setting would be the left hand side is the Galois group, right? So let's say you can compute the Galois group k of f, And by theorem, that is finite group, so it will have finite subgroup. Right? So a finite subgroup. So this finite subgroup is, let's say, H1, H2, up to maybe H something. Okay, and then the right hand side is the intermediate field. Okay, so it's intermediate field. Okay. So this is F, this is K. So this is the intermediate field. And so in order to construct an intermediate field from left to right, the idea is that somebody take a group and then you take the so-called fixed group, right? So you can take the fixed, you can take the, you can take the fix, right? So fix H means that all the element X belongs to the large K, such that the sigma X equals to X for all sigma belongs to H. Okay, so this is a fix, which is a field. And then for this side, somebody give you an intermediate field M, then you can construct the Galois group M over F. And obviously, like by construction, this Galois group will be subgroup of this. Right? So this is all the sigma belongs to this Galois K over F, such that it fixes the field for every X belongs to sigma X belongs to M, which is fixed F. Okay, and the theorem just tell you that these two, so the Galois main theorem will be these two are actually one-to-one correspondence, namely that if you start from the left, you map to right, and you go to left, they will be the same. Okay, so right, so this is the idea. Okay, so now I can use this theorem to, I can try to prove this. Okay, so let's see this proof. So I can say that H is a subgroup of, let's define H is a subgroup of G K over F. Okay, and I can define let's say KH to be its fixed field, right? So let me just write fixed H, K of H, right? K is a fixed field, and I can show that which is I'm going to show is that the order of H is the K over KH. Okay, this is the first one. Second is that H is exactly just Galois group of K over KH. Okay, so this is a one-to-one correspondence that I have, right? Because if you start from H, then you construct KH, and after that you start from KH and take its Galois complement, Galois construction, and you get the same thing. And yeah, this is the main theory. Okay. Okay, so let's see a proof. Okay, so in Hurston approach that I already do some weird that new definition for a normal. So actually this actually if you prove this part, then this part would be completely trivial. Let's see a proof. Okay, so by lemma. Right, so by lemma, I know what? I know that the K is exactly the KH is joined with element A. Right, this is a trick because KH is a subfield, is the intermediate field. So this guy will be normal, right? So K will be algebraic extension over KH. And by this by previous lemma that you finally become just one element. Okay. So this is our starting point. And that's maybe so let's see what so originally we have what? By construction, we already know that KH this, right, is greater or equal to Galois. This is what I already have. KH, right? And I know this, right? Because this is definition. Any fixed group, any H construct, this is almost a definition once you write down, right? So this is originally what you have. So so once you prove these, all the two are the same, then you prove that this what guy belongs to this. Okay, so this is one is just, so we only need one. Okay, so the idea is that that's why we need this. So let's define M to be the degree. So let's say M is the degree of A. And it's a minimum polynomial of degree A over KH. Okay, so let's say you can let sigma to sigma up to sigma H to be the element of H. Okay, and then you can define a coefficient, let's say alpha 1 to be the summation of sigma AI sigma IA, I from 1 to H, and alpha 2 will be the sigma I, sigma J. I is not the same as J, and then you can define a sigma alpha H, sorry, to be sigma 1A, sigma 2A up to sigma HA. Okay, so you can easily check that. You can check, this is a simple check that alpha 1 up to alpha H is invariant under H. Okay, this is almost trivial. You can, because H is you can view that H is a subgroup of Galois group which fix F, but this symmetrize will make it the same, right? Because for example, if you times another sigma in it, then it becomes just permutation of the group. And the same for alpha. So you can define a P of X to be X minus sigma 1A, X minus sigma 2A, up to X minus sigma HA. Okay, so all of these are coefficient, right? You can times this alpha 1, alpha 2, alpha H. And all these, so P of X is a polynomial in the K of HX. Okay, and let's see, right? Because KH is a fixed H, right? So these all these are invariant under H, right? So P of X will be KH of X. Okay, but so this P of X has order H, right? So P of X has order H, but the minimum polynomial of A has order M, and you can check that the P of A is 0, right? By definition. Because all these are roots and the coefficients between the roots, right? So if you put, so this is actually A, right? Because sigma 1, that's if you define sigma 1 to be identity, then P of X will be right, P of X A will be 0, right? So which prove that M is less or equal to H. Okay, so which prove that KH is less or equal to H. Okay, so this is the theorem. Okay, so this is the Hurston's approach to get the answer, and a little bit different from the usual proof. So the usual proof is that if your starting point is to not assume that the character K is 0, and the proof will be much more complicated. Okay, so see you guys next video. So next time I will prove more theorem and connecting the Hurston's normal extension to a splitting field, and then we get our connection. Okay, so see you guys next videos.